Thank you very much for the invitation. It's a pleasure for me to tell you today about WIMP and other rare event searches in these liquid rare gas detectors. And just to set everybody in context, so we are now talking about direct detection. What we do here is that we employ the particles that are gravitationally bounded in the potential of the Milky Way. And those would eventually pass by the Earth, scatter on nuclei of a detector target. And then this nuclei would get a nuclear recoil that deposit energy, something about a few keV, tens of keV. So really, we are talking about a tiny energy deposition. You see here the rate equation in which the main ingredients that we need are highlighted. So the astrophysical parameters, because we have these particles in the Milky Way halo, we need to know the dark matter density at the position of our solar system and the velocity distribution. And then the two parameters that we are aiming at measuring, one is the dark matter mass, and the other the cross-section with ordinary matter that often is separated into spin-dependent or spin-independent. And here you see already like the status of the searches, the spin-independent cross-section and the WIMP mass in the x-axis. And then you see all these colorful curves that represent exclusion limits for not measuring, let's say, these particles. So what they mean is that all the parameter space above the curves is excluded at a certain confidence level, 90% typically. So everything above those lines is excluded. At the bottom, you see this color region. So these are the cross sections at which neutrinos would scatter coherently with nuclei. Solar neutrinos on this region, and atmospheric and supernova neutrinos. And because they would also make the nuclear recoils, they would constitute a background for direct detections. But you see that there is lots of parameter space below the excluded region, and there is where we would like to discover dark matter, ideally very soon. You see that here at the bottom, so the best sensitivities are by liquid xenon detectors or liquid noble gases. So above something like a few GeV, this is the most competitive technology. And then you might ask why, no? Why is it that way? And I think that the key is that with these liquids, you can build very large masses, and then you have also an homogeneous target of the element you have. And you can choose among two detector concepts, either single phase or only liquid, or double phase in which you also have gas, as we will see in a moment. With either of the two, you can reconstruct your position where the interaction happens in 3 dimensions. And this helps a lot. This is what we call fiducialization, because you can select the innermost volume for analysis. And this is the one that is typically cleanest in terms of background, of radiation background. And another advantage is that these novel liquids are transparent to their own scintillation light, meaning that when you're growing in size up to meters of detectors, you are not losing in light collection, so you can go larger without losses of light. Here on the bottom at the left, you see the rate as a function of the nuclear recoil energy for different isotopes, but you could focus on the blue and on the black, which are argon and xenon. A little bit steeper on the xenon because it's heavier, a little bit flatter on the argon. But in all cases, you have this kind of exponential type of spectrum. So it's of high importance to be able to achieve a very low energy threshold in order to profit from this exponentially growing rate towards lower energies. Here I summarize a little bit some characteristics of the 3 liquid novel gases that you could use for detectors. But although neon is also possible, you will see that argon and xenon detectors are being realized. So neon, mostly R&D was carried out. Something that keeps us experimentalists very busy, not only working on liquid novel gases, but also overall in direct detection, is to understand our backgrounds, reduce backgrounds, measure them to take them into account in our background predictions. And here you see a list of different contributions. So we have external backgrounds, starting with gamma activity from natural radioactivity. Of course, you can select very clean materials, and you can use techniques like the self-shielding I explained before, or projecting multiple scatters. Neutrons are quite dangerous because they would also scatter on the nucleus, making a nuclear recoil. For instance, muon-induced neutrons is quite an issue. It is the reason why all these detectors are placed underground. So you see here, the lower, the deeper your detector, the lower it goes your muon flux, and then the lowest probability to have a muon-induced neutron. There are, however, also neutrons from natural radioactivity, alpha N reactions of fission, and also here you can do shielding or material selection as much as you can beforehand in order to have a clean detector. The last contribution of external backgrounds is something you cannot shield, neutrinos. Neutrinos from the sun, from the atmosphere, from supernova, I showed you already before. But one can see this maybe also in the positive side. As the detectors are growing, this would also be a nice signal that those detectors could measure. Now for the liquid novel gas detectors, it's quite important to have a look at the internal background. So those are the ones that are dissolved within the target. Of course, radioactive isotopes within the material you are using. This is quite important in the case of argon, because when you take your argon from the atmosphere, there is argon 39 at a becquerel per kilogram. In xenon, there are in principle also two isotopes that are unstable, but as you will see later, they have such a long half-life that they are actually not really relevant for dark matter searches. Most important is the radon, especially in xenon detectors. We have to make large efforts to reduce radon emanation from the materials, and also krypton-85 is something that we need to suppress. Now I move to the first kind of detector concept, the single phase, in which you have your liquid, typically in a sphere shape, and you have a look at the scintillation light from all 4 pi with photosensors, typically photomultipliers. And this technology has the advantage of not requiring a F3 field, and also having very high light yield because of this very good photo coverage. Pulse shape discrimination can be used to separate between different types of particles. I show you here an example in liquid argon by RDM, where you see an electron and alpha particles, and you see that the fast and slow component have very different ratios, and then you can use that to separate. And indeed, this works very nicely for neon and argon. And in argon, separation up to 10 to the 8 has been reached, for example, by this deep detector. In xenon, it's not as good because these fast and slow components are closer to each other, but it can also be used and has been used. The first experiment I want to talk about is DEEP. It's a detector at Snow Lab in Canada, which is quite large, more than 3.5 ton total mass. And a couple of years ago, they released data of a long run, 230 days. And the figures I show you here are from this data. So here, the Z versus R square, the events in green, and inside the fiducial volume, there are no excess of events, so they could derive a limit. It's the red curve, which is currently the most competitive liquid argon result. You see that is a little bit below Darkside, that we would have a look at it in a moment. Most important is that they took further data from January 2018 to March 2020. This is blinded data, and analysis seems to be ongoing, so we are very much looking forward to learn from that data soon. Also in single phase, but now using liquid xenon. There was the Xmass detector at the Kamioka mine in Japan. It deployed 1 ton of liquid xenon and used 800 kilograms as a fiducial volume. And because of this very good photo coverage, this detector had a very, very high light yield, almost 15 photoelectrons per keV, would translate into an energy threshold of 0.3 keV. So really ideal to go very, very low in WIMP masses. It had a commissioning run, and from 2013 to 2019 had a very long data taking time. And out of this data, lots of results have been derived and presented. I show you here 2 examples, a WIMP exclusion limit here, or an hidden photon or axion light particle limit presented. But the experiment was stopped in 2019, and some groups of Xmass joined now xenon, and they are now part of xenon N-ton. The second technology that I wanted to show is the dual phase. So you have a liquid on the bottom and gas on the top. So the dark matter particle would scatter, and then the nuclear recoil would excite the medium. And from the de-excitation, you have the scintillation light that you can measure in 2 arrays of photomultipliers at top and bottom, typically. And this we call prompt signal S1. And there is also charge, so ionization. And if you place a drift field and with electrodes, you can extract those electrons that are created, drift them through the liquid, extract to the gas phase. And now this is the reason why we have the gas phase. You use it to amplify the signal. You have this proportional signal S2, which comes after the drift time. So this gives you the Z component, and then from the heat pattern on the PMTs, you get the XY. So this is the 3-dimensional position that you can get. And the nice thing here is that for similar size as one, here for an electron or gamma making a Compton effect, or here a neutron making a nuclear recoil, the S2 has a very different size. So you can use a ratio of the charge to the light to distinguish between different types of particles, what we call discrimination. Darkside uses exactly this technology. There is Darkside 50 at LNGS with 50 kilogram that derive in 2018 very interesting results. But since then, they have joined DEEP, RDM, so all the liquid argon worldwide join a global collaboration under the name Darkside 50K. And they want to make a big step going from the 50 kilogram to the 50 ton with a TPC in a seal acrylic vessel read out by silicon PMs for the future. One key aspect for this detector is, you remember I mentioned argon 39 before. So if you use argon from the atmosphere, you would have a constantly rate in your detector that would create too much dead time. So you need to lower that. And actually Darkside 50 could show already that if you take argon from underground sources, because argon 39 is cosmogenically produced, then you can reduce that by a factor of 3,000 or so, maybe even more. And there is a whole plan ongoing in the collaboration. They built an extraction plant in Colorado. They are measuring the depletion factor at Canfranc, and from there, the argon would go to a distillation plant. You see a picture here in Sardinia to lower the argon 39 as much as possible and have the run. These detectors aim at the high mass dark matter search and to be in operation about 2025. There are plans even beyond that. So the sensitivity they want to reach is this red line here, but another factor of magnitude could be reached if you go another of magnitude larger in size. This is the Argo concept. The other idea is to use just 1 ton, but using only the ionization signal. This is also something that Darkside already made before. This is an analysis technique in which you give up on your S1 because the energy threshold for the S2, for the charge signal, is lower than the S1. So by using only the charge signal, you can open sensitivity to lower WIMP masses. And this is also the idea of this other detector here. Beyond measuring dark matter, there are studies ongoing on measuring neutrinos from the sun, xenon neutrinos, for instance, or also supernova neutrinos, and this via the coherent scattering of neutrinos in nuclei. This is a quite interesting measurement because all flavors contribute in the same way, so you would have an integral measurement, flavor insensitive. And with this, I move now to the liquid xenon TPCs, and I would start with the results of xenon 1-ton, which is my own experiment. Here you have the plot again of before cross-section and dark matter mass, and now highlighting the results of xenon 1-ton. So you see our result when we use S1, S2 in blue. The light blue is an improvement on the energy threshold that opened a little bit down here. The green is this charge-only analysis, similar to the liquid argon. And you see that above here, 3 GeV, we have best sensitivities. You see also this migdal curve here. This is to be taken a bit with care. This migdal effect is such that you have a nuclear recall that actually is too low energy to create quanta that you can measure with the energy threshold of your detector. But when the nucleus is moving, the electron shell has to move behind it, and this kind of electromagnetic impulse could create some signal, ionization, excitation, and if this effect would be there, this would be our sensitivity. However, this remains to be proven, and there are few experimental efforts to measure if this effect is there, and in that case, this would be the kind of limit we would have. Something to tell you also is a very interesting signal that we had last year. So now we are not looking at the nuclear recalls, the typical region where we would look for dark matter, but more to the electronic region. This is the, let's say, background dominated, where we have all our contributions. You see here 10 different background that we model. The highest one, the dominating one is lead. This is coming from radon. And everything fits very nicely, the model with the data, besides down here. No? Here the data goes up while the curve goes down. This is not very significant, it's about 3 sigma, but has created a lot of excitement in the community, a lot of papers trying to explain what's seen there. And indeed, this is opened right now, so this could be a new background, maybe tritium, but it could be the onset of a new signal, maybe something exciting, axion or something else. No? So that's why it's currently very exciting to know what future detectors would tell us. And indeed, future looks very promising because we have 3 machines that are able to tell us if this is something interesting. Our own upgrade is xenon n-ton with 6 tons of liquid xenon, but there is the Japanese Panda X 4-ton, and in the US LZ, all taking first data or commissioning in a, I would say, a true race to measure WIMPs down to these very small cross sections. First data from Panda X was released this summer. They achieved a very good radon level. Unfortunately, because they had a contamination with tritium, this coming from a previous calibration source, and they could not test this xenon 1-ton excess. But this is something that maybe you can do in the future. So this is the result that they released. This was a non-blind analysis, but in the future they would go with a blind analysis. And I think you will hear more about this in a talk later, tomorrow. I show you here also data from xenon 1-ton. Is taking data at LNGS. We also made huge efforts to reduce our background and could lower down to 1.7 microbecquerel. And we have also means to bring this down even by a factor of 2. And besides special measuring WIMPs, we of course have as a main goal to test electronic recall excess. For the future, there are the Darwin or E3 plans to go another order of magnitude beyond what xenon n-ton or Z could measure. And the news here is that Xenon, Darwin, and LZ have joined together. We had a workshop together, and out of that, a memorandum of understanding has been signed to go together for the future to build this very large detector that could be in several tens of tons of liquid signal. Now you have this very large multi-ton target, very low threshold and very low background. Ideal to measure dark matter, but that suddenly more and more other physics cases are opening. And I wrote here a summary of all rare events that you could aim at measuring. I'm not covering all of them, but I just pick up 2 examples. I want to start with something that's in a 1-ton measure. Recently, it is a quite rare event. It's a process, is the double electron capture of 124 xenon. So what happens is 2 electrons are captured in the nucleus simultaneously and 2 neutrinos are emitted. And then what you see is the relaxation of the electron shell. So here you see your signal, or our signal that we measure with about 4.4 sigma significance. And actually, this is a standard model process, but the reason why this made it to nature is because of the incredibly long half-life that we measure. Now it's actually 2 times 10 to the 22, 10 to the 22. And this is the longest ever directly measured half-life. And this gives you the feeling that we are now really at the front of measuring things that have never been measured before. So surprises can come anytime, which is of course very fascinating. Kind of the opposite process, the double beta decay. And then we have an isotope, 136 xenon, which decays via double beta decays and is a candidate from neutrino-less double beta decay, which would be a test of lepton flavor conservation. And we have almost 9% of it in the natural abundance of xenon. So you see here the standard model process, and here the neutrino-less case. This 9% means that if you take, for example, the mass that we plan for Darwin, without any isotopic enrichment, you would have 3.5 tons. So it's quite some target. And then you can look for this peak, in this case of this isotope with 2.5 MeV. What you see here on the bottom is this, not only the signal here, but also the backgrounds that we would expect with the energy resolution. So we took the energy resolution that xenon 1 ton was able to reach. And then we get our projection for sensitivity. Here you see for the Darwin baseline, if we have some improvements in backgrounds, then we could get somewhere in between these lines. And you see, of course, dedicated experiments are better, but of course, this is a detector for dark matter. So it's great if we can contribute to this search. Another example would be the measurement of solar neutrinos via neutrino electron scattering. And we have there a window at low energies in which we can measure pp neutrinos with about 7 events also per day. So this is huge statistics, which would allow us to reduce the error bar from the Borexino one at about 10% to 1%. And then you can test non-standard neutrino interactions that could maybe change the shape of this neutrino survival probability as a function of energy. This is one example. Coherent scattering of neutrinos on nuclei, of course, is another option. I think you will hear more about
that. Could you hurry up a little bit?
Later.
Could you hurry up? Yeah.
I'm ready, actually. This is my summary. I maybe just say, so sensitivity is progressing very rapidly. And at the moment for high WIMP masses, the liquid noble gases are leading. And it's getting very exciting. We have 4 devices here that will release results in the next years. And we have even plans for the future to come further. Thank you very much for your attention.